And the new unit is momentum. So momentum. Now we're going to define momentum in the following way. P equals m mass times velocity. And this is a vector. This is a vector. So m mass want to be kilograms. It's velocity. It's a vector. You want to be seconds. And p is the symbol for momentum. Now, units of momentum, there are no specific units or their own. There's no, well, we just have units as such. So we have kilograms times meters per second for momentum. All right. So there's your definition of momentum. And now there are a couple of things that you can do with it. So in the first place, well, let's solve a problem with it. So there's a worksheet, and I think it's the first worksheet that you have there on Canvas, worksheet 1. I'm going to solve problem number 3. And let me copy that problem in here. Let's pause this. So a 2 kilogram ball is moving at 3 meters per second. Find its momentum. Well, so what we have is mass m. Oh, I see. 1 second. Then we gotta do here a bit of go. Now we should be all set. So mass is 2 kilograms. Velocity is, well, really what the problem gives me is speed. Speed is 3 meters per second. But I guess what I'm gonna calculate here is the magnitude of the momentum, not so much the momentum as a vector. But anyways, so p plus times v. And really it's a vector thing, but then I can just write as the magnitude of p mass times the velocity, and let's substitute what I have. So then momentum, its value, its magnitude is going to be 2 times 3, and I end up with 6 kilograms times meters per second. So there's that. That's all there is. Suppose that the problem was stated a little differently. So let's say that problem 3 actually said something like this. A 2 kilogram mass moves at the velocity of seconds, second, or proper, find its momentum. And so in that case, your momentum T would become mass, which times them. Skip the as 2. Have proper units, I suppose. So then I'll write it as 4 kilograms meters minus grams seconds. So this is momentum as a vector, and here on the left hand side you have momentum as if you just magnitude them. Okay, so calculating momentum by itself, that's kind of trivial, not too complicated. Note that momentum in physics actually kind of comes close to what we intuitively think of as momentum. Right? The faster something moves, if you look at the equation here, P equals mv, the faster something, more momentum it has, but also the bigger the mass of that something, as that kind of goes along with the intuition that we have of what momentum is. All right. So now you should pause this video and do problems 1 through I think it was 1 through 7. So do these problems 1 through 7. That's just on momentum, and then come back to the video. Now in the meantime, well, I suppose I'm gonna assume that paused and that you have solved numbers 1 through 7, and so we're going to move on, and we'll move on to impulse. Calculating momentum, that's kind of trivial. Now we're going to add impulse to this whole picture, so I'm going to move my screen. All right, so impulse, I put here impulse. Yeah, impulse. Impulse, we're going to define it, we're going to give it a symbol, J. This is just how I write J. However you write capital letter J, that will be the symbol. J is defined, or impulse is defined as the change of momentum. That's all there is. Impulse is just the change of momentum. Just in case, for the sake of clarity, J is the final momentum minus the initial momentum. That's how we define. That's how we define momentum here. And so, I mean impulse, and so J is, well, impulse. Units of impulse. You have two options. You could either just stick with the units of momentum, or it's Newton. Ooh, what was it? Wait, let me think about it. It's just newtons times seconds. So and you'll see why newtons seconds in a second. But for the moment, let me put it here. If on a test you put it kilograms meters seconds, that's fine. Get credit for that. But the other unit that is proper, and maybe even more proper, I think, is often enough you will see units of impulse in terms of newtons times seconds. You'll see soon enough why that's the case. All right, so we have it. There's the definition of impulse. And because of the definition of impulse, you can end up in a couple places with this thing. So, all right, so now let's go back to this. Momentum is mass times velocity. What we'll do is we'll find, we're gonna find two different expressions for, two additional expressions for impulse. So we have the definition of impulse, but now let's see what we do with it. So here's the momentum equals m times v. Take the time derivative of both sides. So d dt of p equals, to do something to the left hand side of the equation, you might as well do it to the right hand side of the equation. We end up with that, and that gives us, of course, dp dt for the rate of change, time rate of change of momentum. And then mass is a constant, so you can pull this constant out in front of the derivative, and then you end up with dv dt. But now dv dt, that's well, give you a second to think about that. And the second has gone, so what we have is mass times acceleration. Now mass times acceleration, that is just the definition of f net. It's not really well, anyways, mass times acceleration is f net, and so what we have here is dp dt. dp dt is f net, where by f net we mean the sum of all of the external forces acting on an object. For a lot of problem that we'll consider, this is just going to be the force of the collision. So we'll be considering collision. Now we can take it a little farther, and that's what we're going to do, and that is, we're going to, where am I going with this? I'm going to go up here. We can rewrite this like this. F, I'm going to keep F now. This is supposed to be F net. I'll drop that for the sake of clarity. Now let's take the derivative of both, antiderivative, both sides of this equation here, and let's put here boundaries from the final till, from the initial momentum to the final momentum. Pi to pf. I can do that since I have an antiderivative with dp here. And then here I would have some initial time, final time. So what I end up with on the left hand side is, well, pf minus pi. That gives me f dt. Now I'll drop the boundaries, but pi to tf is what I should have. But when you look at the left hand side, that's pf minus pi. That's by definition impulse. So what we have here is that the impulse j is also the antiderivative of the force, the net force acting on an object, dt. And so here's your other equation for the impulse. I suppose what we could do is we could say, here's one first equation, here's the second equation. And the story kind of ends there, although we have a few modifications to do with it. So the first one is that I actually didn't want this to be here. Move it. Let's see. Move this thing. Let's put it right here. Gonna be a better spot for it. And let me go back to All right. So, well, I guess what we, all right. So what this will often become is we're just going to approximate this thing with the following expression. It's some kind of an average force during the collision, AVR, average force during the collision times however long the collision takes, or average force exerted on an object which causes the change of velocity in the object times the time during which that change takes place. Right, so note that this is, there's no equality. This is just an approximation. You can approximate an integral here with some average force times time during which the whole collision takes place. And so what I should do, I should probably kind of extend this like that. In 1201, when I teach this thing, I only show them this equation. But here we can see the whole proper expression. Now, from here, what you can also get is that J is equal to the area. And what do I mean by that? Well, let's take a look at the graph here. Suppose that you have a force exerted on an object and then force versus time. So this is some sort of a net force exerted on an object, and then, you know, let's say that net force, initially there's no net force acting on an object, so the object just goes on at some velocity v, and then there's a change of that velocity v, meaning that there's, well, if there's a change of velocity, there's got to be some kind of force. And say that the force looks like this, from nothing to it spikes and then it goes down, right? And so the result of this force, the velocity vector of the object changes. Now, this whole expression here, that's nothing but the calculation of an area, right? Antiderivative of f net dt. If you put some boundaries here from some ti to tf, which is what it should be, then what you're doing is you're starting at ti, maybe somewhere here, and tf as here, and you're calculating the area under this whole graph. So when I say area, when we say area here, this is what we mean. That thing right there. And one more note. Oh, so this is also going to be the third approach to impulse. So you have three equations for impulse, kind of four actually, because you also have this one. But you have, by definition, impulse to be the change of the momentum. Impulse is also the antiderivative of f net dt, which can be approximated by the following expression: the average force acting on an object times the time during which the force is acting on an object. And then that, of course, here amounts to J equals the area under the graph. So you have kind of four equations. Right, so that's the whole background. And let's also solve some problems. So I'm gonna slide this way. And now we're looking at, what are we looking at? Same worksheet. So worksheet 1. Same worksheet 1, but the problems we want to look at is oh, I got to figure out which problems we want to look at. It's probably just the next ones, whatever they are. Let me find them. All right, so it's problem 8 in your worksheet, and let's see what we have. A 2-kilogram ball hits a wall and bounces back. Its initial velocity was 2 meters per second toward the wall. Final velocity is minus 0.5 meters per second away from the wall. Find impulse delivered during the collision. So let's draw this thing. If I know that the initial velocity, okay, so here's a mass. Let's draw a picture. You have a mass, and the mass is moving in a direction, in a positive direction. So here's positive 2 meters per second. And this thing goes and goes, and it hits the wall. There's the wall. Bounces off the wall, and then it goes back. So let's draw it here. Now its velocity is minus 1.5 meters per second. The signs are important. If you screw up the signs, you will get answers. Plus indicating that it moves to the right, and this is minus indicating that it moves to the left. Since we're in 1D, there's no need for vector notation. Plus and minus implies directions, and so vectors. The mass is 2 kilograms, and the mass stays constant, doesn't change. All right. find impulse delivered. So this is my given, if you will. This is the setup of the problem that I have. And then the unknown is the impulse. Here the unknown is J. Now J by definition is change of the momentum, final minus initial. All of this is vectors. What I have to do is I have to find the final momentum. This F is M I. That gives me 2 times final is 5 so 2, right? Which gives me minus 3 minus 4. Let's make sure we didn't make an error here. Yeah, so this gives us minus is important. 7. Oh, and then the newtons. Let's just keep newton seconds. Oh, and by the way, this actually. So J is that's an ugly J, but anyways, there's your J. That negative implies the direction. It's a vector. It just points to the left. I'm gonna put here left. Points to the left. Newton seconds. Where am I getting that from? I have here Newton seconds right from here. J is F net times F net dt, right? Or average force times time. So what I get from this is from maybe I'll change the colors. From the force I get newtons, and then from the time I get seconds. So you can express units of impulse as newtons times seconds, and this is often enough to newton of the units of impulse. If you wrote here kilograms times meters per seconds, I wouldn't mark. All right, so we have that. Signs are important. If you screwed up the signs, you'd be losing points. Like if on a test you got this as a problem, it's kind of easy, but you could get this as multiple choice question. You don't want to make errors with the signs, so the signs are important. Okay, that was problem 8. Let's see what else we have.